Welcome back to another episode of Who Wants to Be a Mathematician? I'm your host, Mr. Hill, coming at you with some AP Calculus. We're continuing on our journey, and this stop is going to be related rates. Related rates is something that we do when we take derivatives, but we'll get to that in just a second. If we remember from last time, we talked about implicit differentiation, and that's when we took the derivative of a variable with respect to another one. So if we take a derivative with respect to x of y, we're going to get the derivative of y with respect to x. But if we had something like y squared, and we're taking the derivative with respect to x, then we take the derivative of y squared, which would be 2y, times our inside, because we have to do our beautiful little chain rule here, dy dx. So implicit differentiation is going to be giving us these symbols, and that's going to be used a lot in related rates. So we're going to jump right into it. Here we go. So related rates. Related rates are just another step. Before we were talking about slopes, we were talking about velocity, but there's many other useful applications. Related rates is one of them. So we're going to start off slow, take our time going into this. So if we want to find the derivative of y with respect to time, so this is what we want to find, this is simply the same thing as the derivative of y times the derivative 1 over the derivative of time. Or we could think of it as the derivative with respect to time times y. All of these things are valid in how you can think about it. So if we go up to our problem, y equals x squared, what do we want to find? Well, we want to find the derivative with respect to time of this thing. So we're going to take the derivative of y, which is dy with respect to time dt. We're going to get 2x times dx dt. And what do we know? We know dx dt is 2, so this is just simply 2. And we know our x is 3, so this is simply 3. So we have 2 times 3 times 2, which is equal to 12. So in conclusion, our dy dt is just equal to 12. So if we're trying to find the same thing, dy dt, when y is 16, we're going to change it up a little bit. We still have y is equal to x squared. We still know that dx dt is 2, but instead of knowing our x variable, we know y variable. So start off, let's find our derivative of y with respect to time. So derivative of the whole thing, we're going to get dy dt is equal to 2x times dx dt. Well, we know dx dt to be 2. So when we go to our next step, we get 4 times x, but we don't know x. But they did give us y is equal to 16. So if y is equal to 16, we know y is equal to x squared. So 16 is equal to x squared, and x is equal to 4. So then we just plug our 4 back down at the bottom, and we get 16 is equal to dy dt. So kind of just simply plugging and chugging substitution stuff. Pretty basic starting off. So let's do a couple examples of these. Go away. Whoop, just kidding. So if we have L is equal to the square root of s, we want to find ds dt. Oh, I'm sorry, we know ds dt is equal to -3, and we want to find dl dt. So to find dl dt, we're going to take the derivative with respect to time of our L, equals the square root of s. So we have dl dt is equal to, and we know this can be written as s to the 1/2. So when we take the derivative, we get 1/2 s to the negative 1/2 times ds dt. And what do we know? We know ds dt is -3, so we have 1/2 s to the negative 1/2 times -3. And we know L is 4. So if we know L is 4, L is equal to 4, and we know L is equal to the square root of s, we know 4 is equal to the square root of s. So therefore s is 16. We plug that in over here, 16 to the negative 1/2 times -3, so we get 1/2 times 1/4 times -3, which is equal to -3/8. So dl dt is equal to negative 3/8. Whoop. So now we're changing it up a little bit. We got a little more going on in our equation. Same sort of things. We're given dx dt is 1. We want to find dy dt when x and y are 1 and 2 respectively. So to find dx dt, to find dy dt, we need to take the derivative of our function with respect to time. So we have 2y times derivative of y minus, we're going to do our little product rule. Let's do first times the derivative of the second plus the second times the derivative of the first. And derivative of 2 is 0. So now we just put in our information we know. We know y is 2, so we have 4 times dy dt minus, we know x is 1 times dy dt plus y is 2. Dx dt is 1 equals 0. So if we clean this up, dy dt, negative dy dt minus 2 is equal to 0. I just distributed my negative. Then I can factor out a dy dt of 4 minus 1 is equal to 2. I just added 2 to both sides, then factored it out. So we're left with dy dt is equal to 2/3. Bada bing, bada boom, we're done, we're happy. So this next one, you guys work on your own. Pause the video, see if you can figure it out. Know what do you know? 3/2, and you know this. Whoop. You know this. You want to find that, and you also know that. So pause me, do the little problem, and we'll be right back in just a second. Alright, so here we go. You should have paused me. If you haven't paused me, pause me and give it a try. So we want to find dp dt. So we want to find the derivative of p with respect to t. So we're going to take a derivative of the whole thing with respect to time. So we get dv dt is equal to negative 5p, negative 5 times 3/2 p to the 1/2 times dp dt. Little chain rule right in there. Negative 15/2 p to the 1/2 times. And now just fill in the information that we know. We know that dv dt is negative 4. We want to find dp dt. So that means we now need to solve for p. That's the only piece that we're missing. Well, how do we do that? Well, we know v is 40. So we have 40 is equal to negative 5p to the 3/2, negative 8p to the 3/2. Then if we square both sides, we get 64p to the 3rd. Cube root, we get 4 is equal to p. So negative 4 is equal to negative 15/2 times 4 to the 1/2 times dp dt. Now it just becomes algebra. We know this goes to 2, and then this 2 and that 2 cancel out. We divide both sides by negative 15, so we have 4/15 is equal to dp dt. Bada bing, bada boom, and we're done. So you should have gotten this. If you didn't, go back and check your work from step to step to step to step. So let's do another, that's the same one. Let's do this one. So find the rate of change of the distance between the origin and a moving point on a graph. Okay. Well, first, let's figure out what the heck they're even talking about. So if we draw our graph, we want to find the distance between the origin. Ooh, I know where the origin is. So let's plot that. 0, 0. And a moving point on the graph of y equals cosine. Well, I know what y equals cosine looks like. that simply starts up here at 1 and oscillates between 1 and -1, going up like that. So they're looking for a point, just some xy coordinate, and they want to find the distance, the rate of change of the distance between those 2 points. That's a bad arrow. Let's try that again. There we go. So the distance between the origin and a moving point. So we know that we're looking for the rate of change of this distance. And if we reach back to our wonderful days, we know distance is equal to x squared plus y squared. This is also known as Pythagorean theorem. Same thing, you kind of make a triangle. We know distance is equal to our x squared plus our y squared. So our distance is equal to those 2 components. Well, up here tells us a little bit about our equation. We want everything in terms of x's because they don't give us a change in y. So we know that d squared is equal to x squared. Now we just need to get our y in terms of our x variable. Well, we can just simply do that by subbing it in. So cosine of x squared. We solve for d. D is equal to the square root of x squared plus cosine x squared. And we want to find the rate of change of the distance. Rate of, that's kind of crossing out. Rate of change of the distance. This is a key phrase. We know rate of change is what? It's our derivative of the distance. So our distance is just simply our d. We're looking for the rate of change. And what are we looking for if we know dx dt is equal to 2? We know we're looking for in terms of time. So we're going to take a derivative of our whole darn thing plus cosine x squared. So if we take the derivative of d, we get dd dt. If we take the derivative of this other side, we're going to have to apply some chain rule going on. So we got 1/2 times x squared plus cosine x squared to the -1/2 times, we're going to have the derivative of the inside. We have 2x dx dt, and then we're going to add that to the derivative of of cosine squared. So the outside is 2 cosine x. Then we need to multiply by the derivative of the inside, which is negative sine x, times the derivative of the inside, which is x, so we get dx dt. So there we go, our whole shebaggle. And what are we given? We're given dx dt is equal to 2, so we can simplify this whole thing a little bit. So we got 1/2 times x squared plus cosine x squared to the -1/2 times 2x times, this is replaced with 2, so we're gonna back up and make this a 4, because we have 4x plus, we know this one's a 2, so we're gonna make this a 4 cosine x times sine x, and we'll just change our addition to a subtraction because we got a negative sign back there. Right, negative makes that negative. So this is our answer, as crazy as this is, because the rate of change, or our derivative of our distance, is equal to this. So if you give me any point, because it's a moving point, if you give me any point, I can tell you the rate of change of our distance. And that's why you have x's left over in your equation, because they haven't given you a point, so you don't know what point you are on our graph here. So if you give me any point, I can give you a distance. So we're going to continue on with the next page, but we're going to take a little break, so get up, grab a snack, go get a drink, do some jumping jacks, go pet a cat, whatever you need to do to gear up for the next one, because away we go.